Hello, everyone. As Anthony said, my name is David Warde-Farley, and I'm a PhD student at the University of Montreal in the LISA lab. That's a French acronym, so don't bother expanding it. Basically, we study machine learning, this is joint work with James Bergstra, who is a former student of LISA and is now at the Center for Theoretical Neuroscience in the University of Waterloo. So this is a bit of a strange talk. I'm going to start with an overview and a crash course in what deep learning is, and it's made some media landfall in the last little while. I'm going to give you a brief introduction to Pylearn2, which is a library developed in the LISA at University of Montreal. And I believe that that's the first time this work has been presented at SciPy or anything like it. And then I'm going to talk a little bit about hyperparameter optimization, what that is, why we care about it, and specifically talk a little bit about Hyperopt, which is a package written by primarily by James Bergstra. It's been presented here at SciPy, I believe, last year. I'm going to talk about a submodule of Hyperopt that has some interesting interpretations and uses, and I'll talk about how we've taken the ideas in hyperopt.pyll and turned them into a package that we're spinning off as a separate effort. Search Spaces, the package, contains all the code necessary to glue these two very powerful tools together. Finally, I'll close with some future directions. So, basically, who here has heard of deep learning? Let me see a show of hands. Okay, so fairly large subset of you. But basically, the long and short of it is that in traditional machine learning, you're doing some labor-intensive feature engineering and then using kind of a black box. And your objective function in those regards, the function that you're actually optimizing with respect to your training set, is usually pretty straightforward, if not convex. And the learning algorithms are fairly well described in your favorite machine learning textbook. The trouble is that the human is still very much in the loop in traditional machine learning practice. And a good human can make or break the performance of your system. There's also, I've left scalability as a question mark because a lot of the algorithms that were in vogue in the 90s are not really the most scalable things on Earth. Obviously, there are large-scale approaches to machine learning that involve learning linear models online and things like that. So a blast from the past is something called neural networks. They were popular in the 1980s, but they have a bad rap, or at least they did for a long time. They were supposedly prone to overfitting. Not really. You just really stop on a validation set. That's been known for years. Your objective function is non-convex, so that means that you may have lots of local minima. In fact, you're guaranteed to have lots of local minima due to symmetries. Is that really a problem? As you'll see, probably not. The main thing is that there are lots of design choices that are kind of black art, especially using many hidden layers, so many layers of neurons in between your input and output that are used as features used to be very, very hard. And so here we've got a neural network that has a single hidden layer. And you can think of these as sort of feature detectors that are then weighted in linear combinations and then pass through some nonlinearity at the output. For a long time we wondered, why couldn't we deal with deeper networks? Why couldn't we train them? The training always seemed to fail. They were always a very attractive approach because rather than having the well-paid or underpaid grad student or well-paid consultant sit there and engineer features for you, neural nets seem to be able to learn features very easily. In the diagram, I've shown features, that is to say, linear filters of the input learned on some handwritten digits by an unsupervised algorithm. Learning features, and especially learning hierarchies of features, seemed like a pipe dream that was too good to be true. Because very deep neural networks, they never really worked, with a couple of exceptions, convolutional nets being one. Training seemed to always get stuck. Until around 2006, you may have heard the name Geoffrey Hinton tossed about. Essentially, this guy at the University of Toronto figured out one way of training very, very deep neural networks. People at NYU and UDM soon followed, and now we have generally an idea of why. And briefly, Jeff's approach used a greedy layer-wise approach to stack single-layer modules, but this soon became fairly out of vogue, and now we can just train the whole thing. So just for a stab at a definition, deep learning, I would say, is the study of machine learning systems that employ multiple levels of representation that form a hierarchy, but where we don't specify the semantics of those representations a priori, where we learn those features, and we learn the representations between, or the relationships between them. Deep learning is important. Basically, it's completely blown the field of speech recognition away. Better acoustic models have translated to much more usable systems. And in computer vision, the same thing has happened. You're now seeing commercial products based on deep learning that employ these sorts of techniques to, automatically tag your photos and things like that. And it's not just machine perception tasks which are seeing a benefit. My friend George won a Kaggle competition with deep nets concerning predicting drug targets and things like that. He has no background in this area, but the machine learning methods were powerful enough, and the regularization was good enough that essentially we didn't need them anymore. How does this thing work?
The red button.
Red button? Oh yeah, okay. Yeah. And Vlad and me did the same thing with predicting job salaries for a UK company called Adzuna with precisely the same bag of tricks. I'm not going to really harp on that, on the details too much, but the catch is that it's an active area of research, and it was basically abandoned for 10 years, so we're still playing catch up. And there are a lot of hyperparameters, so knobs that you specify a priori that can basically make or break your training procedure. These are somewhat problem dependent, and you rely a lot on heuristics and practitioner know-how. The machine is doing more of the learning, but the human is still perilously in the loop. Enter Pylearn2. Now, Pylearn2 is our software effort to try and develop a platform for experimentation. So we're still trying to tease apart how these algorithms work, what makes them work, and publish papers about them. It's been developed mostly by the students you see here, and also tons of other contributors from Lisa and elsewhere. It's built on top of Theano, which is a mathematical expression compiler that's been presented a couple of years ago at SciPy. It's been used for lots of cutting-edge research, and it's actually being used in industry, we found out recently, in the Bay Area for a machine learning as a service startup. You may have heard of scikit-learn. A brief overview of the differences in philosophy. Essentially, we are a platform for researchers, and we want to configure and tweak all the things, whereas scikit-learn just wants to bottle them and make them accessible. And both have their merits, but this is what we're trying to do. And we're also targeting GPUs because neural net algorithms tend to love GPUs. So rather than just having one estimator object as you do in scikit-learn, our experiments can roughly be broken up into a hierarchy of objects. One is just a training harness that sort of deals with the outer loop logic, a training algorithm, a data set, and a model. And you also have all sorts of, ancillary objects. And the reason we do this is for modularity and configurability and reusability. We ended up using a configuration language other than Python. I don't really remember the reason why, but suffice it to say, this has become the popular way of using our library, which is to say a YAML file that describes an experiment from top to bottom as a DAG of objects, and there's just a common script interface to actually execute the experiment. I guess the original motivation was to separate config from implementation to make your research more reproducible and to sort of set up a couple of roadblocks to doing really crazy hacks in the heat of the moment that are prone to bugs. And you can, but I should add that this interface to the library is completely optional. You can just use straight Python code. And the way that this is parsed, it works exactly like you'd expect. It instantiates this object with these keyword arguments. Now, I had said that deep learning algorithms have a lot of fiddly knobs, and we tend to refer to these as hyperparameters. Parameters being the quantities that your model learns during training, hyperparameters being the things that you set prior to training. Anyone with experience in machine learning knows that you can just grid up your hyperparameter space. sklearn or scikit-learn has facilities for that, but it can be very, very slow and very inefficient. And James Bergster had a paper in 2012 that argued you're actually much better off doing random sampling. And this gets you around several inefficiencies with respect to some parameters not really some hyperparameters not really meaning much or interacting much with others. But random search and grid search are both really naive, really dumb. And so you might rightly ask, can we do something better? And the last couple of years of research on the topic suggests that yes, we can. In particularly the formalism of Bayesian optimization, wherein we use a machine learning model, such as a Gaussian process or a regression forest, to learn an approximate mapping of hyperparameter configurations to performance on a held-out validation set. So here there's a cartoon that was drawn up by Nando de Freitas of an actual objective function and a surrogate model that has learned I believe this is a Gaussian process that has learned a mean variance for each point in the space. And these are three different criteria that are often employed for essentially optimizing these, for picking a new point. Now, Hyperopt is briefly a package that implement some of these strategies. Importantly, it can handle conditional hyperparameters, which are very important in deep learning, where you may have some parameters that don't mean anything in some contexts. And the general interface to Hyperopt is an fmin function that takes an objective function, a space, an algorithm, and a maximum number of evaluations. The objective function is pretty standard. The algorithm is just a sort of a switch to tell you which search strategy you'd like to use. But what about the space? And that's where things get interesting. So space can be any nested sequence or dictionary structure, but it can also incorporate delayed function calls. This can be a nice way of shoving hyperparameters into your deeply nested structure after the fact. And as you'll see, arithmetic and get item operators are all overloaded, and you can do conditional subgraph evaluation with choice, a function provided by the library. And deferred evaluation is really, really powerful abstraction for this kind of metaprogramming. Basically, we should all just be using Lisp, but nobody really takes that seriously anymore. Okay, fair enough.
Bonjour for the win.
So the way that pyll works, which is the Hyperopt submodule, which defines this mini language, is something like that. Hyperparameters are specified with this sort of syntax, which defines a prior distribution, and you can do arithmetic on them and things like that. And you've got a couple of deferred function calls here. So when it came to me that I wanted to use Hyperopt with Pylearn2, my options were sort of limited. I could either use templated YAML files, or I could write a new wrapper for every experiment I wanted to run. And we know how I felt about that. But it became fairly obvious that we have one system that produced DAGs and another system that consumes DAGs. So why not just, shove one into the other? We thought about using pyll for this, but it, for a variety of reasons, is very tightly woven into Hyperopt. And there are some other design choices that we wanted to avoid, so we rebuilt it from the ground up. In particular, we noticed the similarity to functools partial, and we basically extended this into something that we uncreatively named partial plus. Similarly, we retooled the interface for specifying free variables and provide a function for evaluating the deferred evaluation graph. And that's just some example code, which I don't know if I have time to go over, but essentially you have two variables x and y that are nested inside a list, and when you evaluate them, you can sub in arbitrary values. And this can get pretty complicated pretty quickly. Once we have this common interface language, all we need is one set of code to import the Pylearn2 experiment DAGs from a YAML script or YAML config file, and one set of code for targeting pyll as an output format. And so I don't really have a whole lot of time, but if you can see that, that's, oh, what the heck? That's basically an example config file. I won't really have time to do the demo I wanted to, but that's basically the idea of the approach we took. I've been traveling a lot, so I'd actually like to start using this after actually writing it. We're going to support other hyperparameter optimizers, not just Hyperopt, and also incorporate some really exciting new work about doing parallel training. Thanks. I'd like to acknowledge NSERC. James is supported by a Banting Fellowship, and we also were getting some collaborative grant money from D-Wave. Thank you.